Okay, let's go through some practice problems with triangles. Let's start with some sequence of problems. We're going to keep using these same triangles. So if you want to write them down on a piece of paper, we're going to use them for the next 3 or 4 problems. Let's start with the triangle T1 and T2 given by these elements and compute what are the barycentric coordinates of the point 0, 1.5 with respect to both of these triangles. So we're going to do 2 different problems. Pause the video now, work through what all of those are going to be, and see if you can figure out the barycentric coordinates in both the first triangle T1 and this triangle T2. Okay, so there's 2 ways you're going to solve these. We're going to start the first couple to help build your intuition more graphically. So I like to start by sketching it so I understand what the problem I'm asking for. And once I draw the first triangle, I can notice that the point I'm asking about, 0, 1.5, is on the line from 1, 1 to minus 1, 2. It's in fact halfway on the line. So as soon as I recognize that, the barycentric coordinate of the third element, v, has got to be equal to 0. So now I've reduced it from a 3 unknown problem, u, v, and w, to just u and w. And now I have to simply find the 2 by 2 solution to 0, 1.5 is u times 1, 1 plus w times minus 1 and 1/2. I can put that together in a matrix and go ahead and solve it, although you can actually see without a lot of work that you can just multiply each of these by a half and you get that answer, because a half, these two cancel each other, and then a half times this gives us 1 1/2. So second, for the triangle 2, first drawing it out, we see it's this right triangle, origin minus 1, 0, 0, minus 1. And again, the point 0, 1.5 is sort of special. It lies on the line, but not on the triangle itself, but on the same line as the edge formed by Q1. Therefore, again, it's going to have 0 for one of its components. The other 2, again, you build a simple linear system. It's pretty straightforward to see that they're going to be 2.5 and 1.5. So again, you can solve these sort of graphically. Let's do another one where we're going to go ahead and try and solve that. And again, we can do it graphically. This time we're going to want to do it a little bit more algebraically. So we take the same triangle and let's say, what are the barycentric coordinates of the point 0, 0? So hopefully if you want to solve it graphically, we again can look and say the point we're interested in this time happens to be on this edge. These are very special constructions. So given that w is equal to 0, you reduce it to a 2 by 2 problem. Okay, we can again solve that 2 by 2 problem similar to what we did before and get the answers of u is 2 and 1. If that's not obvious how you do all of that, wind back up to the broader solution. To figure out u, I would take the determinant or the determinant of P2 minus P1, the area of P2 minus P1 divided by the area of P2 minus P1. Sorry, there's a P up there. And that gives me u, and then I can go ahead and solve for v. In fact, if I was writing code for this, all these special cases are complicated and generally not going to happen. So the real solution is to just form the area of P1, P2, P3 divided by the area of P1, P2, P3, right? So just the area of the sets of points. Right here we have the point P, 2 and 3. Here we have the point P, 3 and 1. Here we have the area of point P, 1 and 2. And so I can do all these by determinants, and that gives us the solutions. In fact, you only have to do 2, and then the other just comes from subtraction because they always have to add up to 1. Okay, one last, again, special case just to make sure you get these, because sometimes this is actually can happen where the point you're looking for is a vertex of the triangle. And since it's a vertex, I don't have to do any math. Everything is always just 1, 0, 0. It's on a vertex. If it had been on this vertex, it would have been 0, 1, 0, and so on. If you're on the triangle, that element is 0. If you're on a vertex, that element is 1. So let's go back and try something simple again. Given the triangle, compute the centroid. Come back to the video after you've computed the centroid for both triangles. Okay, in barycentric coordinates, the centroid is always just 1/3 of each of the components, so it's 1/3 of the sum of these of each of the vertices, which gives us the centroid. And I can also look at it as 1/3 for the first point plus 1/3 the second point plus 1/3 the third point. In this case, it gives us these 2 points. If you're not sure that those are the things, go ahead, graph it out. You'll see that that really gives us the centroid of the triangle. Okay, so now we can ask another related question. What are the areas of T1 and T2? So how big are these triangles in terms of their areas? Think about the general solution and then solve it for this problem. Okay, so welcome back. So for this, the area for these is just given by the determinant of P2 minus P1 and P3 minus P1, which is 1/2 the determinant of this, which is 1 minus 1/2, gives us, times 1/2 out in front gives us 3/2. Now this one's not special. It did have to be P2 minus P1. It could have also been P2 minus P3, and then this one would be P1 minus P3. You make a vector from subtracting any points. You make one the base, subtract the other two, you get vectors. Take the determinants, and that gives us the area. Similarly for the triangle 2, if we make 0 the base, it's easy. The subtractions just go away, and we get 0 minus 1, 1, 0. Take the determinant, we get 0 minus 1 is 1, and of course the 1/2 out in front gives us 1/2 as the total area. Again, it's actually a right triangle, so for that special case you can check that's 1/2 base times height. It's easy. Okay, let's do one more slightly more complicated question. Let's take the affine map given by this matrix problem here, where we have the matrix A, 1, 2, minus 1, 2 times x, and add in the value minus 1, 0 for our translation, for our affine transformation. And now ask the question, or set of questions, what's the area of triangle T1 and T2 after mapping? So we're going to get two new areas, and then compare the ratios T1 over T2 before and after mapping. Go ahead, work that out. Come back to the video after you've got your answer. Okay, welcome back. Hopefully you did not solve this by taking each of the 3 points, multiplying them, adding them, getting values, and then doing the area formula we just covered. Hopefully you remembered that since we're doing a linear map, the area after transformation is just the area before transformation times the determinant of the map. The addition doesn't change area, only this part does. So we can just take the determinant of this map, which is 2 minus minus 2, so it's the determinant is 4. So whatever we started with before, we end up with an area that's 4 times that after the mapping. And so in terms of the ratios, we just can take the area before and after, which was 3. Multiplying the top and the bottom by 4 doesn't change anything. It's still 3 as well. And so we get this is unchanged, and the areas are just 4 times what they were before, giving us our final solution. So hopefully you didn't have to look up too many of these as you were going through them. If you did, please go to chapter 17 of the book, look at some of the example problems at the end, and for a whole bunch of them, the answers are at the end, so you can work your way through until you can get through these problems without having to look at the formulas each time you do it.